This is the 9th lecture of the course MTH 204A for section B. Recall that in the last lecture we have defined the irreducibility of group actions. So, for a group action for a group G acting on X, we said this action is irreducible if there is no non-empty proper G invariant subset of X. As an example, we saw several examples, and one of the examples was the following, that for any group G and any subgroup H, G has a natural action on G modulo H. So, this is the set of all left cosets of H in G. So, the action is defined in this way, G comma XH, this goes to GXH for every G and for every X. So, this action is irreducible. In this lecture, we will first prove that this is the only type of irreducible actions of G. So, what I mean by this is, given any reducible action of G, this must be same as, I am putting the word same between quotes. So, given any reducible action of G, irreducible, then it must be same as the action of G modulo G or action of G on the left cosets of H for some subgroup H. So, in order to prove that, first I have to precisely define what I mean by two actions are same. So, we start with the definition of G invariant maps. So, from now on, let me just introduce not any new terminology, the same thing but in a different way, just another way of saying that. So, if G acts on X, for our convenience we will simply say X is a G space. Okay. X is a G space, and sometimes instead of writing this, we will also write this. The first one will be the set, the second one is the acting group. Okay. So, given that we have given two G spaces X and Y, by a G invariant map between them, I mean the following, that has to be a map. So, a map F from X to Y is said to be G invariant if for every G in G and X in X, one has the following, F of Gx is G Fx. Do not get confused this with composition of mappings, because here F is a function map from X to Y, whereas G is an element of the group. So, we can depict that in the diagram, that from X to Y we have this map F, and you know that for any group element G, we have this map given by X is being mapped to Gx. Okay. Similarly here, so we have this map that each Y is being mapped to Gy. So, we have these two maps which we loosely call multiplication by G from the left. So, saying G is invariant is equivalent to say that for every G this diagram commutes. Okay, for every G this diagram commutes. Let me give you a quick example of a G invariant map which is important in our context. Look at this. So, from let G be a group from G to G, and from G to G modulo G to the set of all left cosets of H in G. So, here we have this map sending each X to its coset. Okay, both the vertical maps are the same. Now, we see that this map, that which is the quotient map, is G invariant. How to see that? That is obvious from the definition. Each G sends X to Gx, and the quotient map now sends X to Gxh, and now you see that this is exactly where you reach if you now act, if you now let the group element G act on this element Xh. Okay. So, this is an example of G invariant map between two G spaces. Okay. Let us make some observations regarding G spaces. So, first of all, so what are the observations? If A is G invariant, then so is f of its image. Okay. That is direct verification, hence I am leaving that to you as an exercise. Similarly, we have the in some sense the opposite one, that is if B in Y is G invariant, then its pullback is also G invariant. This is like the first one, this is also easy to see. Maybe for you I can just directly show, I can do this for you just to show that it is indeed just indeed a direct one. So, if Y is in F inverse B, then Fy will be in B. Now, we want to show that Gy, we want to show that Gy is in F inverse B, therefore, we have to apply F on Gi. So, F of Gi is nothing but G of Fy, which is already in B. So, as I said, this is a direct verification. Okay. So, from this it follows that, so maybe I can record that as the third one. So, if Yg is irreducible, then F has to be onto. Why? Because this is quite clear, because so if we in the first one, if we take A to be x, then f of x, which is the image of x, which is the range of this map F, will be a G invariant subset. Certainly this cannot be empty, because F is non-empty. Thus from the reducibility of this action, f of x has to be y, which is same as saying F is onto. Okay. Note that it is also quite, at this point it is also quite tempting to say that if x is if this is irreducible, then F has to be 1 1. That is not true. A counter example for this is this one. Both these are irreducible actions. However, this map, this G invariant map is never going to be, this G invariant map is not going to be 1 1 unless G is trivial, unless H is trivial. Okay. So, this is not true that irreducible, this is not true F is 1 1. Okay. So, we see this. Now, let us make the definition here. The definition of going to G spaces will be regarded same. So, if a G invariant map, okay, so I mean this is just the notation for any map between two spaces. Now, if this is G invariant, sometimes we denote this by simply saying F G x to F y G. So, G is written in the throughout just to tell us that the map is G invariant given to G spaces. If this is 1 1 and onto, then we say, then we call F an isomorphism. Okay. So, if we have a G invariant, if F is a G invariant map which is both 1 1 and onto, then we can say F is a isomorphism between two G spaces. It is easy to see that if F is isomorphism, then F inverse is also isomorphism. Okay. And if between two G spaces, if there is an isomorphism, we will say those two G spaces isomorphic. Thus, we have defined, so as usual that when there is an isomorphism between two G spaces, we will regard them same. So, now we have defined what we mean by two G spaces are same. In view of that, the main result that we want to prove in the first half of this lecture is, given any reducible action of a group G, it is isomorphic to the action of G on the left cosets of H for some subgroup H. This is what we are going to prove. Okay. So, in order to prove this, let us make these general observations which will immediately lead us to this theorem. So, what are we doing here is the following. So, we have recall that if we are given an onto map from a set X to a set Y, then from this onto map we can produce a 1-1 onto map considering the following quotient, right. So, how is this map defined? F tilde x bar is defined as f of x for every x. Okay. So, we are going to do the same in case of G spaces as well. So, now we are given two G spaces x and y. Suppose we are given two G spaces and F is a G invariant map. Okay. Assume that it is onto. So, therefore, we have let us draw a bigger diagram to depict that. We do have F. Okay. Now, from the G invariance we are going to consider this x mod tilde. So, on x we define a relation that x we define x is related to y if and only if f x equals to f of x equals to f of y. So, this is an equivalence relation, and then the quotient set by this equivalence relation is the set of all equivalence classes. Okay. So, since this map is G invariant, we will see that this quotient can also be made a G space in the most natural way. So, for that let us observe that if x and y are related, then f x equals to f y, of course. Then for any G, for all G, then of course from the G invariance property of f for all G. So, what does this tell us? Well, G. So, if x and y are related, then gx and gy will also be related if f is a G invariant map. All right. So, therefore, this shows us we can immediately make this x mod tilde a G space. How? That is very simple. For any x bar belonging to x mod tilde and any G belonging to G, we denote, we consider this Gx bar. So, this is a map from G cross x mod tilde to x mod tilde. It is easy to see that this map is well defined in view of this. So, thus x mod tilde also becomes a G space very naturally. Okay. So, given any G invariant map between two G spaces, we can form the quotient. Okay. So, now we will show that this G space is isomorphic to the G space Y. So, it is same as saying there is a bijection between. So, this is just the analog of this phenomenon in the context of G spaces. Okay. So, that is actually quite easy to see. Let us first draw a bigger commutative diagram. So, this square, yes, this square, let's draw f somewhere else. So, f is the vertical map. So, what is the map here from here to? This is the usual quotient map, sending each x to x bar, and now you can easily see that for every g, this square commutes, and of course, from here to here we have this f tilde, same as here, and again this square also commutes. Why? That is quite easy to see. Let me do the verification for you. So, for any g, so take a typical element from here, it looks like x bar. So, x bar, if x bar lies here, f tilde sends x bar to f of x. Now, by g it goes to g of f of x. This is nothing but f of gx. Now, you see x tilde goes to gx, x bar goes to gx bar, and by f tilde gx bar comes to here f of gx. Since f of gx equals to g of x, we see that this square also commutes. And since by our concept we have already seen that f tilde is a 1-1-on-2 map, and we have just checked that f tilde is G invariant. Hence we see that x tilde. So, this map f tilde, well, maybe we can put this in this way, x tilde g, and is an isomorphism. Okay. So, this is a very general phenomenon which we have just discussed, that given any onto G invariant map, then the quotient formed from this, the quotient formed by this map is isomorphic. So, that can be made a natural G space, and that G space is isomorphic to this given one. This is what we have just proved for any G, any X, any Y. All right. Now, let us come to the special case for this, which will prove us the desired one. So, okay, so let me put it in this way as a corollary. If assume Y G is this G space is irreducible, then for every, then for all G space xg and G invariant map F, the previous this happens. This is simply because of that if Y is irreducible, then any G invariant map has to be onto, which we have already observed is irreducible, then x tilde G is isomorphic. Yes. The second corollary is will give us the theorem which we want to prove in this lecture. So, remember the previous diagram. So, let G be any given group and H be any, okay, let G be any given group, and and let X be this be irreducible G space. Okay. So, therefore, we do have the irreducible G space. Recall that if a G in the last lecture or maybe last to last lecture, yes. So, what we have seen is if this is irreducible, means for any x in x, many x in x, yeah. So, in the last lecture we have seen this is nothing but the whole of x. Okay. So, in view of this, what we will do is let us fix some x in x, fix some x in x. Now, once we fix that, we can consider this map from G to x, sending each G to Gx. okay, for every G. So, in view of this irreducibility, we see that this map has to be onto. In fact, we will prove that this map is actually a G invariant map. Let me draw that diagram and that will make everything clear. So, here we consider two systems. The first system is we regard G as a G space. So, the action of G on G is by left multiplication. So, the first G space is the action of G on itself by left multiplication, and second G space is X. Let us verify. So, verification is actually quite straightforward. So, the map sending each G to Gx, and so this map here also the vertical. So, both the vertical maps are this map. Now, it is easy to see that for any G prime. So, G by left multiplication, G, if you start with a G here, G goes to G prime G. So, now by this map it comes down to G prime Gx. On the other hand, here if I apply multiplication by G prime, that is if we consider the symmetry given by the group element G prime, then we see that it will go to exactly G prime G of X. Therefore, by chasing this diagram, we see that this map is in fact a G invariant map. So, it's a G invariant map, it is an onto map. Therefore, we can apply this general observation in this context, and what do we get? So, we have to see in this context how this relation tilde looks like, and then consequently how this quotient looks like. So, that is actually quite easy to see. What we do is G1 and G2. If both G1 and G2 are being mapped to the same place by this map, if both G1 and G2 are mapped to the same place by this, then we must have G1 x equals to G2 x. From the property of action, this is same as saying G inverse 1 G2 inverse G1 fix x. So, therefore, two elements will go to the same place by this map if and only if they fix the chosen point x. Now, it is easy to see that for any given y. So, this is a rather a general definition, I should make it separately. Let us say if xg is if this is a G space, irrespective of whether it is reducible or irreducible, then for any x, the following collection, that is collection of all group elements which fixes x, is indeed a subgroup of G. Okay. So, this subgroup is called stabilizer of, the nomenclature is very natural, stabilizer of x in G. In our context, we will rather, temporarily we will denote this by Gx, because writing this notation it's not so convenient. If we need to write this quite frequently, this is not so convenient. So, in our context, let me denote that by Gx. So, for any x, this is a subgroup, the stabilizer is a subgroup of G. So, now if we come here in this situation, what we see as G2 inverse G1 belonging to the stabilizer of x, which is equivalent to saying that G2, the coset, these two cosets are same. Okay. That immediately tells us that in this context, x mod tilde is nothing but the, so in this context, x mod tilde, so in this context, x mod tilde is nothing but the set of all left cosets of the stabilizer of x. Okay. Okay, that is fine. So, then what does that give? This general observation, that is let me rather draw a bigger diagram. So, this is this. Okay. So, we have just applied this in this context, and therefore, thus we get an isomorphism between these two G spaces. What is the isomorphism? So, a typical coset goes to, so let me write down the isomorphism clearly, that is better. So, any typical coset G typical coset by this isomorphism goes to Gx. So, as I said that from this general phenomenon, it as a consequence of that, it follows that Xg, the given irreducible G space is isomorphic to this G space. So, thus every reducible action is basically action by left multiplication on the collection of left cosets for some subgroup. So, up to isomorphism, thus we establish that up to isomorphism, these are all the irreducible G spaces. Okay. All right. Before I go further, let me give some further consequences of this. So, if we remember further consequences of this. So, if in the special case when G is finite, in the special case when G is finite, for special case when G is finite, of course, then X also has to be finite, because X is nothing but for any X is nothing but this. When X is an irreducible G space, if G is finite, then so like between these two sets we do have a bijective mapping, right. So, therefore, when G is finite, this is also finite, this is also finite. So, their orders must be same, and here the order is exactly the index of the subgroup, which implies that okay. So, whenever we are given an irreducible action, this is what we obtain. And again, considering a further space, well, let me do it in this way, that so this is what we see for any reducible G space. Now, as a consequence of this general phenomenon, of this general observation, we obtain the following, that if this is a G space, let X be any set, or let Xg be any G space, let Xg be any G space, then for every X in X, we consider the orbit of X, and automatically we have the subaction of G on the orbit of X, which is irreducible. So, as an immediate consequence of this, we obtain that order of G is same as order of this subgroup times order of this orbit. So, for any X, the order of the number of elements in the orbit times the order of the stabilizer of X is same as the order of the group G. So, this is called the Orbit-Stabiliser theorem. So, this is nothing but a very special case of this isomorphism called the Orbit-Stabiliser theorem. So, this theorem enables us, when G is finite for finite groups, this theorem enables us to count the number of elements in the orbit if the stabilizer is known, or count the number of elements in the stabilizer if this. So basically this is the product of this. So whenever two things are known, then automatically the third one will come out of that. Okay. So in particular, if for an action we know for a typical element, if we know the order of the stabilizer and the number of elements lying in the orbit of that, then from that we can count the number of count the order of the group. Okay. So let me show you this by an example. So consider the regular cube. Consider the regular cube, and then we consider the group of the rotation group for this cube, that is the group of all rotations which by applying those rotations the cube will be mapped to itself. Okay, the rotation. So this is my x, and G is the rotation group of the cube, group of all rotations of the cube. So the group of rotations indeed acts on the sides, acts on the faces of that cube, right? Because whenever we apply some rotation, each face goes to some other, face, maybe the same one or maybe different. So basically the rotation group acts on the set of the faces of this cube. Now you see, given any face, we can geometrically we can see that we can, if you start with any face, you can send it to any other face by appropriate rotations, right? So therefore each face, for every face, the number of elements for every face, the order of its orbit is 6, because we have exactly 6 faces. And then we see that given any face, the number of rotations which are going to keep that face fixed is 4. Okay. Because these are just the rotations, only 4 rotations will keep any given face fixed. So thus from that we can immediately calculate that the rotation group of this cube has 6 into 4, 24 elements. So as I said, that Orbit-Stabiliser theorem, in many we will also see many times later on that this actually this counting formula actually helps us to count either this or that several times in practice. So this is a very useful combinatorial formula which helps us to count. Okay. Another example which is also quite important in this context is the following. So let us consider this action. So let G be, as usual, let G be a group. Let G be a group. Further assume that P be a prime. So therefore, and assume that G has order P to the power L for some positive integer L. So groups having order some power of some prime are called P groups. So thus we started with P group G, and let G acts on X. So the general form of class equation tells us that X will be, okay, and assume also that X is finite. X is the set of all fixed points under this action, and let these be the non-trivial orbits. Okay. So what do we get from this? So if we take any non-trivial orbit, the order of the orbit is nothing but the index of any of its stabilizers. So therefore, well, at this point I should leave this following exercise to you, which I forgot to mention, that suppose G, we have a G space if x and y are related, that is well, if gx equals to y, then find the relation between gx and gy. So, show that they are conjugate. Gx, gy are conjugate. Okay. So, thus if we take any element from an orbit, then the stabilizers will always have the same order. Anyway, so for each we see that each order of each non-trivial orbit is a divisor of order of g, okay, divisor of order of g, which is p to the power t. So, the non-triviality of each y ensures that each of these summands from here to here will be divisible by p, okay. Now, if, so since each of these terms, each of them is divisible by p, so p divides this if and only if p divides x, okay. So, from this it follows that if p does not divide order of x, then p cannot divide this. In particular, this cannot have, in particular this cannot be 0. So, thus the action will always have a fixed point. Then the action always has a fixed point. So, what we have thus observed is, if a P group acts on a set, acts on a finite set whose number of elements is not divisible by P, then the action will always admit at least a fixed point. And as a special case of this, we obtain the following. Special case of this, we obtain the following, that if G is a P group, consider the action of G on itself by conjugation. Okay. So, you see that the orbit of 0, orbit of identity is always identity, orbit of identity is a singleton identity. So, we can simply throw it out and instead consider the action of G on the set of all non-identity elements in G by conjugation. And so, G has order p to the power L. So, this G, so this has order not divisible by p, therefore, the action will have a fixed point. So, what is a fixed point under this action of conjugation? So, if Gx, G inverse is x for every G in G, then that is same as saying x lies in the center of G, right? X lies in the center of G. Therefore, we see that, so thus the fixed points here are precisely the points in the center. Hence, we thus proved Zg is non-trivial. So, what we have proved is, for any P group, its center has to be non-trivial. That comes as a special, as a consequence of basically this counting formula, which is commonly known as this Orbit-Stabiliser theorem. Okay, so I think this is enough for now for actions. Now we move to representations. As I have already said that in this course, whenever we talk about some concepts concepts for general actions, we look for its formulation in the context of representations. Similarly, whenever we prove some result for general actions, we will try to see its version for representations as well. So, let us do that. Alright, let G be a group. Okay, for our context, we can, whenever necessary, we will assume, or mostly we will assume G to be finite. So, let G have a representation on a vector space. So, V is a vector space over F, if we constantly assume A, R, C. However, very soon we will be only considering all the vector spaces for representations, all the vector spaces are over C, but anyway. So, let this be a representation. We simply say this by saying that V rho is a representation of G. We have defined the irreducibility of representations. So, now analogous to what we have done for actions, we will now define G invariant linear maps between two representations. The definition is actually quite simple. So, given two representations V rho and let us say W theta, a G invariant linear map is a linear map. So, it is a linear map T from V to W, a linear map satisfies that rho G of V, that is same as phi G of TV for every G in G and V in V. We can see this by means of this diagram like earlier. We can see this easily. So, from V to V, W, for each G we have rho G, here for each G we have phi G, here we have T. If for each G this diagram commutes. So, it is very natural to ask that whether given two representations there is a there is a G invariant linear map or not. Of course, the trivial example is the trivial map. However, we do have a mechanism to construct a G invariant linear map from a given linear map from V to W. So, what I mean by this is the following, that if let us say S is just a linear map from V to W, I do not know, I do not care whether it is G invariant or not. From that we can construct the following map S tilde, which you can easily see to be G invariant. Well, here as I said that we assume G to be finite. So, we define in this way that T compose rho G compose phi G inverse for G in G, okay, for G in G. This we can immediately see. So, this is immediately seen to be a linear map from V to W is G invariant. So, I leave this verification to you. So, given any linear map, the S, so the S tilde is G invariant. Okay. And in particular, if S itself, which we begin with, is G invariant, then you see that this entire S tilde is nothing but S. Okay. So, if S is itself G invariant, then in this process we are not going to get anything other than S. Anyway, so we come to the analogous results for G invariant linear maps. So, if T is a G invariant linear map, then it is easy to see that. So, this direct verifications I am leaving to you as exercises. So, image of T is G invariant, image of T is a G invariant subspace of W. Similarly, now here we are like this image was also there in case of general actions, but in case of in this linear setup we do have another natural invariant subspace of W, which is kernel T. Kernel T is G invariant. Okay. And immediately it follows that if this is irreducible, then T has to be onto. If T is not provided, it is not provided, T is non-trivial. also if it is an irreducible representation of G, then any non-trivial G invariant map has to be onto. Similarly, if this one is irreducible, then either T is 1 1. So if V rho is irreducible, then either T is 1 1 or either T is 1 1, that is the case when it is trivial, or we have of course so either the kernel is totally V or T is trivial. Okay, these are the easy consequences, and then of course like that of actions we can talk about, we can pass through quotients. So recall that if V is a representation of G, and if we have a G invariant subspace of V, then automatically we get a representation of G on or a representation of G on this quotient space V modulo K. And from linear algebra we know that so all these are what I am going to say. You can see that these are the analogues of the familiar results of linear algebra in this setup. So when we are just given a linear map, no G invariance is there, then V modulo kernel of T is isomorphic to image. So basically the same thing we will also see here. So given a G invariant linear map here. Okay, so before that I should say the meaning of isomorphism, which is very natural. If a G invariant linear map is both 1 1 and onto, then we say that there is an isomorphism between these two representations, and whenever there is an isomorphism between two representations, we will say the representations are isomorphic. Okay, so given that, okay, so let me give you some general some general situations where we have isomorphisms between representations. So let me leave that as an exercise to you. Okay, so let V rho be a representation of G, and W be G invariant, is be G invariant. Well, so yeah, let's assume G is a finite group, which we will now from now on we will throughout assume. So we have already seen that if this is the case, then we do have then there exists a G invariant subspace W prime such that this happens. So now show that the subrepresentation on W prime is isomorphic to the representation, the quotient representation on this V mod W. I am leaving this to you as an exercise. So those quotient representations are indeed up to isomorphism nothing but subrepresentations. Like in case of usual linear usual vector spaces, the quotient spaces are actually isomorphic to the complementary subspaces. So the same thing is going on here. Okay, so this is an example of an isomorphism which we do have, in the in generality, and okay, so maybe I should move on. Yeah, and okay, let's take another exercise which is also quite obvious. So given a G invariant linear map, then in one step we can show that the representation on, so representation of the group G, of course, the representation on V mod kernel T is isomorphic to the subrepresentation on image of T. The same proof goes. So, began T and then the same proof goes. Now, this is again isomorphic to some sub-representation of V. So, for altogether we see that given any G invariant linear map, the sub-representation on the image is isomorphic to some sub-representation of G, the representation of G on V. The given representation of G on V. That follows if we couple these two. Okay, let us rather go to the main content. So, now we look at this. So, what does it tell us? What does it say? It says that, like in view of putting these two things together, if both are irreducible, maybe you can record that as a proposition. If both are irreducible, then if we take any G invariant map between them, so if both are irreducible and T is G invariant, then either T is trivial, okay, or if T is non-trivial, then in one hand T has to be 1 1, on the other hand T has to be on 2, so therefore T will be an isomorphism. So, if two irreducible representations are given and well, here also, here at least here we do not need G to be finite. Yes, we do not need G to be finite. So, if two irreducible representations are given, then any G invariant linear map between them is either going to be trivial or it has to be an isomorphism. Then either T is trivial or it is isomorphism. Okay. So, between two irreducible representations, this is what we are going to see, that any G invariant, two irreducible representation, for any two irreducible representations of G, either they will be isomorphic or T or the trivial map is going to be the only G invariant map between them. Okay, so that is what we see. So, if they are not isomorphic, then the trivial map is the only G invariant linear map. Okay. So, this is what we see in general. Now, for the rest we will assume that V is for the rest we will simply assume that V is a vector space over C. So, let F be C, V is a vector space over C. V is a vector space over C, and of course, we let G to be finite. We let G to be finite. Well, is that necessary? Let us see. If necessary, then we will consider, otherwise not. So, and of course, let V rho be an irreducible representation. Okay, here I should assume that the dimension is finite, is an irreducible representation of G. So, finiteness of G does not seem to be required right now, but let us see. So, and if T is, let T be a G invariant map. So, G invariant endomorphism. So, let T is a G invariant endomorphism, that is a G invariant map from V to V, linear map from V to V, V to V. Then so this is a finite dimensional complex vector space, and T is a linear map from T is a linear operator on the finite dimensional complex vector space. Since C is algebraically closed, it will have an eigenvalue. So T has an eigenvalue. Okay. So consider the map T minus, so let us say this is lambda, say lambda in C. So we will finish soon. So T minus lambda from V to V, of course we have rho G. We consider T minus lambda I. Since T is G invariant, it is easy to see that this map is also G invariant, okay? And this is an irreducible representation. So there are only two ways: either this is trivial, it is going to be an isomorphism, but T has but lambda is an eigenvalue of T. That means the kernel of this map cannot be trivial. So therefore this forces that T minus lambda I has to be 0, which is same as saying T is equals to lambda I. So what it shows that for a finite dimensional representation of a group, here the group need not be finite, but dimension of the representation has to be finite, and it has to be over C or in algebraically closed field. So for any finite dimensional representation of G, these are the only G invariant linear operators, right? These are the only G invariant linear operators. So I mean, coupling this with that, we have the following situation. If for two representations V rho and W phi, if the representations are so for any two so if these two representations are non-isomorphic, then if they are non-isomorphic, then any G invariant linear map has to be trivial. If they are the same representation, then any G invariant linear map must be of this form. I repeat, for any two representations V rho and W phi, we have the only two choices if they are non-isomorphic. But this part is again, as I said, for this part, so this part also, we do not need G to be finite, and here the dimensions are also allowed to be anything. So if they are not isomorphic, then trivial map is the only G invariant linear map between them. And in the second case, if the representations are same and in fact finite dimensional over C, then these are the only G invariant linear operators. So this proposition coupled with this fact is called the Schur's lemma. So remember, Schur's lemma just says that for two representations, if they are non-isomorphic, then there is no non-trivial G invariant linear map between them, and in the case when the representations are same and furthermore, so finite dimensional representations over an algebraically closed field, for example C, then these are the only linear, so these are the only linear operators. So as a mere consequence of this, we obtain the one or two things, and with that I will finish. So given two representations V rho and G and W phi, V rho and W phi, by LG VW, we mean the set of all linear G invariant linear maps from V to W. You can easily verify that this is a vector space. In view of the Schur's lemma, what we have obtained is this is either trivial, when this not isomorphic to phi, and this is just C when rho equal to phi if of course the field is over C and dimension V is finite. Okay. Later on we explicitly later on in this course we see that we can explicitly compute its dimension from the dimension of V, and we can explicitly compute its dimension. So this is what we obtain in view of Schur's lemma. Thus in this case this is a one dimensional vector space, otherwise it is always, and when they are not isomorphic it is always trivial. This is one. Another thing we so this is one corollary. With one more corollary I will finish. So so let us look here. If again come to this case, so when rho and phi are not isomorphic, that is what I mean by the representations are not isomorphic, then for any S for any linear map from V to W, S tilde must be 0, because S is a G-invariant linear map. Note that even if S is not 0, even if there is a non-trivial linear map, but when we make it G-invariant by this, then it has to be 0. And in the other case, if rho equal to phi, of course we assume the field is here C and dimension is finite, then what about this S? Then S tilde is simply rho G inverse S rho G. So consider the trace of both the sides. What is trace of S tilde? Trace of S tilde is the sum of the traces of all these. By choosing some basis, we can see that all these matrices do have trace, do have the same trace, that is the trace of S. So therefore we have trace of we do have trace of S. Okay. So these two operators have same trace, and in view of Schur's lemma we have this has to be some multiple of identity operator. Therefore from here we obtain that this lambda is nothing but, so what is that, if S tilde is this, then the trace of this will be lambda, the dimension of V times lambda. So thus dimension V times lambda is trace of S. So lambda is 1 by dimension of V times trace of S. So in the case when rho is phi, and of course this is the finite dimensional representation of our algebraically closed field, we can in fact compute what this operator is. This is namely the trace of the given operator divided by the dimension times the identity. Yeah, so this is what like from Schur's lemma this becomes just immediate. Otherwise, you see there is no way to prove this. Okay, so I think with that I will stop this lecture.